So we want to review that one because this is probably considered the most important type of sampling because it's the one done most often. The stratified sampling, that's when your sample reflects the population, okay? Let's just keep it really simple. Let's say in a certain group of people, exactly half of the people are men and exactly half the people are women. Let's make it really, really simple. Then any sample that I do, half the sample should be men and half the sample should be women. If I have a sample where, let's say, 75% of the people come from one group and 25% come from a different group, then my sample should reflect that. So let's do a really simple example. Let's say at a particular college, everybody at the college, every student at the college can be broken down as first year, second year, third year, or fourth year. Now, what if you're a fifth year? Well, then you're usually counted with the fourth years. In other words, if you're in your 11th year, you're probably still called a senior. So you're still called fourth year. So everybody's broken down into this. And let's say at this college, 30% of the students are first year students. Let's say 26% are second year students, 24% are third year students, and 20% are fourth year students. And that's actually pretty close to what most schools are. There are always more freshmen than there are seniors because people might drop out along the way. So let's say at a particular school, this is the breakdown of the student population. Keep it real simple. Now, you want to conduct a sample that has something to do with that school. Maybe it's maybe it's going to be they're going to put a new library on campus, or maybe it has something to do with they're going to put a new parking structure on campus. They're going to do something that affects all of the students. And you'd like to know, what do the students think about this? Now, I'm going to give you an example. Quite a few years ago, you guys may not realize this, Mesa College, up until into the 2000s, it was up until Arnold Schwarzenegger was governor, I believe it was $13 a unit. You might find that hard to believe. Into the 2000s, it was still only $13 a unit at Mesa College. Now it's, what is it, $46, I think. Now, the thing is, that money never paid for your classes. That money goes into the state's general fund, like the DMV or anything else. And then the state's general fund then turns and distributes it to the college. That money doesn't even pay for the computer time necessary to keep your roster going. But because we needed to raise revenues, they raised that number into, it was like $36 up until maybe 6 or 7 years ago. And then they made it 46 because, again, they were trying to do stuff. So when it was $13 a unit, we were talking about building a new parking structure on campus, but that money, didn't exist. So to pay for the parking structure, they would have to raise student fees a little bit, and then that money would go to pay for the parking structure. And so they polled the students, and the students overwhelmingly rejected it. And I asked my students, I said, why would you reject that? And they said, well, because we're not going to be here when it's built. And I said, wow, that's kind of short-sighted of you. That's kind of like saying, I don't want to protect the environment because I'm not going to be on Earth when things start going wonky, or I don't want to do all of these things because it's not going to affect me. I said, you have siblings? Maybe you have children someday? In other words, all the future generations would benefit, but the students said, no, I don't want to pay an extra, and it was going to be like an extra $3 or $4 per unit. I don't want to pay for that because I won't be here to reap the benefits of that. And I was actually kind of surprised, but that was the idea. But it was the same sort of situation. They did a poll of the students. So now let's say you've decided you want to do a poll and you want the sample size to be 100. Let's keep it real simple. You're going to poll people, but when you walk around campus and you see a student and you walk up and say, do you want this? Yes or no? Let's keep it real simple. You don't know what year in school they are. So usually what you do is say, do you want this? Yes or no? What year in school are you? That's okay, because otherwise you don't want all 100 people to be seniors. You don't want all 100 people to be freshmen. Can anybody tell me, when you do this poll, what breakdown should you be looking for in your random sample of students? Anybody want to try that one? You're going to poll 100 people. Exactly how many freshmen should you be asking in that sample? Exactly. Anybody?
30.
How many sophomores?
26.
Keep going.
24. 20.
That's it. That's a stratified sample. That's it. There is absolutely nothing else that goes into it, but if you used any numbers other than those, it's not stratified. It means you've over and underrepresented certain groups. Oh, so my sample had 50 freshmen in it, but there's not 50% freshmen. So a stratified sample is the percentage of the population should be exactly the same as the percentage of your sample. That's it. So the problem I gave you in class, I gave you, here's this many from this many groups. So once you knew the percentage, and it came out really nice numbers, by the way. And some folks said, oh, okay, let's just say hypothetically, 37% are from this group. So 37% of my sample should be this. Sometimes you're given the percentages, sometimes you're not. Sometimes we'll say the college has this many students, some big number, and this many of them are freshmen, this many are sophomores, this many are juniors, this many are seniors. Okay, then I got to get a calculator, the number of freshmen divided by the number of students. Now I have the percentage, and then that many out of 100. Now, what if it doesn't come out in a nice exact number? Well, you can always round, but that again should match that. That's it. That's what stratified is. There's nothing else to consider. In the quiz that we had, the majority of the answers said just pick the same number of each group. Well, that's not stratified. That's not even like stratified. That's saying if I have 100 people and 99% are one type and one is the other, I'm going to ask the same number of each group. Well, no, I'd ask 99% from this group and 1% from the other group. Now, the other was the systematic. That's the phone book problem I talked about. And that's where you'd count by the same number of people. A lot of folks started by saying, well, I'd first determine how many people there are in San Diego. No, that has nothing to do with it. Absolutely nothing to do with it. I want to basically make up a number, any percent, 1%, 2%, a tenth of a percent. Then basically that means 1% is 1/100th. It's 1/100th. So you ask every 100th person until you run out of people. That's it. That's the problem we did in class. If I said 2%, that's 2/100ths or 1/50th. So then I'd ask every 50th person. If I said 1/10 of a percent, that's 1/1000th. Then I'd ask every 1000th person until you run out of names. That's what systematic sampling is. And that is often done by people who want to just find out random polls. A number of years ago, and I'm talking, this is 90s. Think of, has anybody here never actually been on campus? Is there anyone here who's never physically been on campus because you're brand new to Mesa? Or you've not had classes on campus yet? Is there anybody in that position?
I haven't been there yet.
Oh, our campus is getting cooler and more beautiful every year. A number of years ago, okay, Mesa College is considered one of the finest places to be, but we had the absolute worst campus. I taught classes in old Quonset huts. Those are the old World War II little metal containers that, they were borrowing these things. We didn't have a lot of buildings. Our campus was old and archaic. Our labs were borderline unsafe because they were from the early 1960s and we're still using them in the 90s. So there were Prop N and Prop S, it was called. It was a, what do you call it? A bond issue, San Diego County, and then the money was going to build new buildings. I mean, it was millions and millions and millions of dollars, okay? So the math and science building that I work in and teach out of, which is spectacular, that was, one of the buildings built. There are new buildings all over campus that are from this. But back in the 90s, before any of this happened, they had to poll San Diegans to find out, will you guys actually support this? Is this something you'll actually do? Because we're going to be raising taxes for a while in order to pay for this. And it's the same thing. A lot of people will say, no, I'm never going to benefit from this. But what about your kids? What about your other family members? What about everybody else in the county? Well, the measures passed. And so for the last, oh my goodness, it's been 10 to 15 years, we've been doing constant construction on campus, building new buildings and updating things. And our campus is becoming a spectacular place. It's modern and it's wonderful, but they had to conduct polls. And so the polls were usually telephone polls all over the county to ask people randomly, are you going to support this? Because rather than put it on the ballot, because it costs a lot of money to do that, they want to find out, is it even something people will vote for? So they did random phone calls. They did a systematic sample. They'd start in the phone book and then they just counted down. And so they asked me, and here's the funny part, the poll took a while, and the last question they asked me on the poll, and it was probably like 45 minutes long, the phone call. And I was happy to answer all the questions. And the last question they asked me is, do you or anyone in your family work for the district? And I said, yes, I do. And they said, oh, well, then we cannot count your response. So 45 minutes of my life was wasted in this interview and polling. And I said to the person, I said, maybe you should have led off with that question. Maybe that should have been the first question. Do you or anyone in your family work for the district? Because that made me biased. Absolutely made me biased, because I'm guessing anyone who worked for the district was going to say, yes, we want this. But I just found it ironic that that was the last question they asked, not the first. But that was a systematic poll, and they asked thousands of San Diegans, and they found that support was actually pretty heavy, which was very, very cool. Okay, so it actually is done. But that's it. Everybody had the easy time with, a simple random sample. That's literally names in a hat. That's the easiest one of all. Today, we're going to start talking about probability, which is actually one of my absolute favorite subjects. Now, the mathematics of gambling is 100% about probability, but probability doesn't mean we're gambling. But the mathematics of gambling, you have to understand probability. Otherwise, you won't understand how any conclusions are drawn. I'm going to explain those things. We're not going to learn how to gamble. I don't want anyone taking a trip to Vegas during the course to try out their new skills. No, it's not like that. If you're a gambler, you're a gambler. I can't do anything about that. I'm not going to talk you out of it. But if you're a gambler, you'd rather be making wise decisions than poor decisions, I'm guessing. So probability. So there's a whole bunch of stuff we have to define first. Probability. Here we go. So here's a situation. I'm going to give you some very statistical situations. Okay. In North Claremont, about a mile from Mesa College, Genesee and Balboa. Okay, those are two streets that intersect. And if you've been on campus, you probably know where that is. It's not very far. It's a major intersection, Genesee and Balboa. Yet when I'm on Genesee, because I usually am driving that way, I'm on Genesee heading north at Balboa. And there's a turn light for people turning onto Balboa. And when my light turns green, I would say on average between 5 and 10 cars will run the turn light before anybody can actually go. Every light, every hour, every day, year in, year out. I've never seen anything like it. It is almost an automatic that people will continue running the red light for a while. So I asked class a number of years ago to conduct a statistical experiment and see if you could come up with the average number of cars that run that light. Well, how would you do that? Sit there at that light, maybe for an hour. Not sit in your car. I mean, maybe stand on the corner, and every time the light, changes, just count the number of cars and do this through several rounds of lights. And then say, what is the number of cars that pass? But this is basically an experiment on probability. You can't say mathematically, oh, I can tell you exactly, the probability that somebody's going to run the light. No, you observe. And this is what you observe every single light. Other situations, and people do this in the city, there are certain lights that appear to take forever. Some of you may be subject to some of these street lights. I remember one a number of years ago. I believe it was Pomerado Road, and I'm trying to remember the cross section. It might be Poway Road. It was, I believe, and I actually did this statistically. I sat through, multiple lights and timed it. I believe it was 4 minutes was the minimum that you waited at that light. It was 4 minutes between green lights at one particular light. That's kind of ridiculous. But the only way to make conclusions is to actually observe repeatedly. This is a form of a probability experiment. I have a coin in my hand, and I believe it might be a Harvey Dent coin. Does everybody know what a Harvey Dent coin is? It's a Batman reference. Everybody know what the Harvey Dent coin? Say it if you know what that is. Nobody ever saw the Batman, the one I think with the Joker. Yeah, that one. It's a coin that's tails on both sides. So you pretty much know what it's going to land on. I have a coin that's, I think is not a fair coin. I think it lands one side way more than the other. How could I ever know this? Do I take a saw and cut it in half and then measure it and weigh it? Or maybe just flip it a whole bunch of times and count heads and tails. And if the heads or tails happen ridiculously more than the other, maybe I suspect something's going on. So a probability situation, you first have to have what's called the experiment. You have to say, this is what I'm actually going to be measuring. I might be counting the number of cars that run the street light. I might be counting the number of tails of a coin flip. I might be rolling the dice and looking at the outcomes, the sums of the dice. And I'm going to do this over and over and over and over again so I can see what's happening. Okay, so you define the experiment so you have something to start with, so you have something you can actually count. Then you have something called the sample space. Now, this is huge. The sample space is the list of every conceivable outcome. Now, we're going to talk about each of these things. So, for example, we'll keep it really simple. I'm going to flip a coin. Here's my experiment. I'm going to flip a coin 2 times. I'm going to flip a coin 2 times. That's my entire experiment. What are my possible outcomes? Well, it can either be a tails or a heads. Okay, so if I flip the coin 2 times, one outcome can be head followed by head. That's one outcome. Another outcome could be head followed by tails. Another outcome could be tails followed by heads. Another outcome could be tails followed by tails. Are there any other possible outcomes if I flip a coin 2 times? Anybody? Yes or no? Is there anything else that can happen if I flip a coin 2 times? Or have I covered all my bases here? Anyone?
Bases covered.
Bases are covered. Good. That's it. So my experiment was flip a coin 2 times. This is called my sample space. It's a list of every conceivable outcome. Now, we like it in an experiment, by the way. We really like it when everything in the sample space is equally likely to occur. That's not always the case, but in the case of a coin flip, if it's a fair coin, not a Harvey Dent coin, if it's a fair coin, then we agree that every one of these is equally likely to occur. I'm just as likely to land heads as I am tails. So the sample space is a list of every outcome. Now, the next thing we define is something called the event. That sounds kind of funny. The big event. If the sample space is the list of every possible outcome, the event are the outcomes that I am interested in. In other words, I flip a coin 2 times. Maybe I'm only interested in the times it lands tails. That's what I'm interested in. Or I'm interested in how many times did it land exactly 1 tail. That may be what I want to count. So the event is the set of particular outcomes you are interested in. The event could be the entire sample space. The event could have nothing in it. It's everything in between. So I have, let me erase this part. My experiment, I'm telling you what I'm going to do. In this case, I'm going to flip a coin 2 times. Sample space, every possible outcome. The event, the outcomes you are particularly interested in. So now we say I'm going to write it this way. The sample space we often just call big S, just to make it easy on ourselves. And the event we'll call big A. We often just like using big capital letters. It just makes it easy. So the sample space might be every outcome of 2 coin flips. The event might be the outcomes that have exactly 1 tail. Okay. N of S, that looks very mathy. That just means the number of outcomes in the sample space. I'll call it the SS. Okay, the number of outcomes. I'm just counting how many outcomes are there in my sample space. NA, that's the number of outcomes in my event. Okay. So let's define what we just did very specifically. Okay. I'll use the 2 coin flip example. We are going to flip a coin 2 times. We said the sample space, and we often write it, by the way, we often write it using set notation. That's actually kind of a formal way of writing it. So we said heads, 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 tails, tails, heads, tails, tails. Let's call the event, what is it I want to count? I want to count the outcome with exactly 2 tails. So that would be that one right there. So event A would be tail, tail, okay? That's the only outcome in event A because it's the only outcome that has exactly 2 tails. How many things are in S? Well, the number of things in S, I believe we all agree would be 4. There are 4 possible outcomes altogether. The number of things in A is just 1. There's only 1 thing in A. We can now formally define the term probability. And it's exactly what you think it should be, I'm guessing. So the notation that we use, because we're lazy, we don't like writing long things out. So I'm going to write it in words and then I'm going to show you the notation. So if I said the probability of event A occurring, that's how we say it. The probability of event A occurring, we just write like this. P of A, probability of A. And that is equal to the number of things in A divided by the number of things in the sample space. The definition of probability, again, is the number of outcomes in the thing you're looking for divided by the number of possible outcomes there are altogether. So in this experiment, can anybody tell me what the probability of rolling 2 tails is? Or flipping 2 tails, I should say, not rolling 2 tails. It would be exactly what? Anybody want to try it? How many outcomes had exactly 2 tails? How many outcomes were possible altogether?
0.25.
Well, leave it as a fraction first. It is always okay to change to a decimal, although probability is rarely expressed as a decimal. We say probability is 1/4, which is 0.25. Problem is, what with 3/7 or 9/13 or something icky? It's a little trickier, but 1/4. Oh, so if I flip a coin 2 times, the probability that I get exactly 2 tails is exactly 1/4. Okay, that makes sense. Now, what's the probability I get exactly 2 heads? What do you think? That would be the same as 0 tails, by the way. What's that probability? Anybody? What's the probability in this experiment I get exactly 2 heads?
1/4.
1/4, yeah, same. Now, what's the probability? I'm going to flip a coin 2 times. What's the probability I get exactly 1 tail? What's the probability I get exactly 1 tail? That's different, isn't it? How many outcomes have exactly 1 tail? 2. So exactly 2 tails, we said the probability was 1/4. Exactly 0 tails, that's 2 heads, we said the probability was 1/4. What's the probability that I get exactly 1 tail?
1/2.
1/2. Oh, by the way, have we covered all our bases? You can get 0 tails, you can get 1 tail, you can get 2 tails. Those are all the possibilities. Do you agree?
Yes.
But notice, tell me about the probabilities. We said 1/4, 1/4, and 1/2. Anything special about those 3 numbers? What do they add to? 1/4, 1/4, 1/2. What do they add to?
1.
1. Coincidence? Hardly. No, they kind of have to add up to 1. Oh, okay. So let's write that down. In this situation here, we're going to write down, and to make it simple on ourselves, let's say we're going to count tails. Okay. This is the experiment. I'm still only doing 2 coin flips. So what I have is, I'm going to write the outcomes vertically. I'll put number of tails Do we agree that you can get 0, or you can get 1, or you can get 2? That's it. You can't get 3 tails. You only flipped it 2 times. You can't get -4 tails. It can't really get negative. Can you get 1.3 tails? No. No, I can only get 0, 1, or 2. This is what we call a discrete count. Remember, we talked about discrete versus continuous. I can get 0 tails, I can get 1 tail, there's nothing in between. So this is a discrete number because I'm counting how many. You just told me a moment ago, I'll put probability. Probability you said was 1/4. You said for this one, it's 1/2. Think of that as 2/4 if it helps. And the probability here was 1/4. These 3 numbers add up to 1. They have to, because I've covered all of my bases. There's no additional outcomes. The probability of your experiment, if you look at the entire sample space, the probability of everything has to add up to 1. It can't be bigger than 1, and it can't be negative. Okay, so that's what we have. If I did this as a histogram, which sometimes is very helpful, my possible outcomes are 0, 1, 2. Instead of frequency, which is what we did before, we're going to put probability. So let's say that's 1/4, then that would be 1/2. And on my histogram, the probability of 0 you said was 1/4. So like this. Remember, halfway between is always good. This guy goes up to the top, and then this guy goes here. So this is the histogram for the probabilities as opposed to the histogram for the frequency. We often find a histogram for probabilities to be better because then it doesn't matter how many times I did something, I can see the visual. I'm exactly twice as likely to get 1 tail as I am to get 0 tails or 2 tails. Now, there's nothing complicated about this problem, but we're translating outcomes and what we say are likelihoods. So if I ask everyone in here to flip a coin 2 times, before you start, do you know exactly what your outcomes are going to be? No, you haven't done it yet, but you know exactly what your outcomes can be. That you do know. Everyone here knows exactly what they can get, and that's what you can get. Therefore, when you do it, okay, now I can see my outcomes. So one of the things I've asked you to do on one of the quizzes, I said, go ahead and just do it a bunch of times, or roll the die a bunch of times, write down your outcomes, and then draw a little picture of what you saw. No 2 people should have the same picture, by the way, because each time you do it, it starts over. The funny thing is, let's say I flip a coin and I just do it over and over and over again. Do you think it's very likely that I flip, 20 tails in a row? Is that very likely if I have a fair coin to go 20 in a row tails? Anybody think that's very likely? Or is that probably not very likely? I'm going to flip a coin 20 times and I got 20 tails in a row. And it's probably not very likely. It's about 1 in a million. Okay, it's about 1. I'm going to show you how to calculate that. It's about 1 in a million. Okay, now just ironically, you flipped a coin 19 times and it's been all tails so far. Now you're going to do it the 20th time. What do you think the probability you're going to flip a tails on that 20th flip is? It might surprise you. You've already flipped 19 straight tails. Okay, now you're going to do 1 more. What's the probability that one comes out to be a tail? Anybody want to guess?
100%.
Well, couldn't it be a heads?
It could.
I'm going to flip a coin 1 more time, fair coin. What's the probability it's going to be a tail? Turns out, still 1/2. It was 1/2 every time I flipped it. And here's the funny thing, a lot of people don't realize, the coin doesn't have any memory. It doesn't remember that it's landed tails a whole bunch in a row. So each time I flip the coin, it's brand new in terms of the coin. Every time you roll the dice, it's brand new. The dice don't remember what they landed. There's no little computer chip in the dice that says, okay, I've been landing this, I got to change to something else. That's the way probability works. Every time I flip that coin, it starts anew. That's why it doesn't matter what your first flip was. The second flip is equally likely to be heads or tails. Then if I did a 3rd, a 4th, a 5th, each time it's equally likely to land heads or tails. Now, if I flip a coin a whole bunch of times, most of you would logically argue that, I should be getting heads about half the time and I should be getting tails about half the time, and you'd be correct. You'd be correct. When I flipped the coin 2 times, the most likely outcome was this one. But it wasn't the only outcome. I could have got this one. I could have got this one. The most likely was half. And we're going to see that. We're going to mess around and play with things like this just so it makes sense to us. So the definition of probability, once again, is the number of outcomes in the thing you're trying to count over the number of possible outcomes that are all together. Okay, so here's a really simple example. On the quiz relating to this, I believe I asked you to flip a coin 3 times and write down. No, actually, no, I'm sorry. I asked you to do it 4 times. So head, 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 tail, 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 write down all the outcomes. So let's do the same problem again. And now I want to do, let's say 3 coin flips. And I like coin flips because they're easy to understand and certainly easy to count. Okay. So here's what you're going to do. You're going to flip a coin, and we're doing this what's called theoretically, 3 times. I want to find a probability distribution for the number of tails. Okay, I'm going to flip a coin 3 times. Anybody want to tell me what are the possible numbers of tails I can get? If I flip a coin 3 times, how many tails can I get?
3,
Or I can get 3, or I can get
2,
2, or
1,
or
0.
do you agree those are all the possibilities? I can get 3 tails or 2 tails or 1 tail or 0. Do you all agree those are only possible? I can't get -2, I can't get 7. I'm going to flip a coin 3 times. I could get 3, I could get 2, could get 1, could get none. Do you think all of those outcomes are equally likely? Oh, that's the tricky part. Are they all equally likely? At first glance, you might say yes, but maybe not. I don't know. So what we're going to do is write down the sample space. Now, if the sample space were absurdly large, we don't write it down. We just calculate how big it is. And we're going to learn how to do that over time. But right now, the sample space is not very big. So we're going to write it down. Okay, so I'm going to call S my sample space. So let's write it down. And we're counting tails. Okay, we're counting tails. So I'll go heads first. I can go head, 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 tail. Head, tail, head, head, tail, tail. Tail, head, head, tail, head, tail. Tail, tail, head, tail, tail, tail. These are all my outcomes. Notice I did not repeat any. I kind of did this in an order that made sense. So head, 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 tail. Head, tail, head, head, tail, tail. Tail, head, head, tail, head, tail, 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 head, tail, tail, tail. These are all of the ways, if I flip a coin 3 times, that these coins could land. There are no other ways. There's no missing ways. Exactly how many ways is this? Anybody? Exactly how many outcomes are there in my sample space here?
8.
8. If I flip a coin 1 time, how many outcomes are there? Heads or tails? How many outcomes?
2.
2. We just did it 2 times a moment ago, and when we counted them, we had 4. I just did it 3 times, and I got 8. Does anybody see a pattern here? 1 time the answer, but there were 2 outcomes. 2 times, if I flip a coin 2 times, there were 4 outcomes. We just did it 3 times, and we counted 8 outcomes. Anybody want to guess how many outcomes if we flipped it 4 times without writing it down?
16.
16. And by the way, here's an easy way to think about it. Take every one of these outcomes and either put a head after it or put a tail after it. Oh, so if I put a head after every one of these, that's 8. But if I put a tail after every one, there's another 8, that's 16. 32, 64. Yeah, there is an actual clear pattern going on there, which is kind of cool. So if I said flip a coin 10 times, Could you tell me the number of outcomes? If you want to say it's 2 to the power, that is actually
32.
correct. Well, if it's 1 time it's 2, 2 times was 4, that's 2 squared. 3 times was 8, and you just told me 4 times was 16. That's 2 raised to the 4th power. So if I did it 10 times, it'd be 2 to the 10th. Remember a moment ago when I said 20 times, it'd be over 1,000,000? If I raise 2, I'm going to show you this, to the 20th power, that's exactly how many possible outcomes if I flip a coin 20 times. Yikes, that's over 1,000,000. Oh, the numbers grow really fast, and I'm going to show you how to do all of them. You never do this in your head. You don't need to. So these are all the possible outcomes. So what we want to do now is create a probability distribution, just like we did a moment ago. And I'll put number tails, the number of tails, and here the probability. So we said before we started that you could get 0 or 1 or 2 or 3 as the number of tails. These were the only possibilities. So now let's write down the probability of each of these. All right, 0 tails. Which outcome or outcomes have 0 tails? Do you agree it would be that one? That's the only outcome that has 0 tails? Everyone? By the way, I do want you guys to be vocal, then I know you're not sleeping. So yes or no? Is that the only outcome that has 0 tails?
Yes.
Yes.
So if there's 8 possible outcomes, then every one of these probabilities has to have a denominator of 8. Because remember, the number in my sample space we said was 8. So no matter what the question is, the denominator has to be 8 because that's the number in the sample space. So the probability of 0 is 1/8. Okay. Now, 1 tail. Do I have any outcomes with exactly 1 tail? Well, there's one. Are there any others? Well, how about that one? 1 tail. Are there any others? Well, how about that one? Oh, how many of these outcomes have exactly 1 tail then?
3 out of 8.
Beautiful. Oh, I love that answer. 3 out of 8, so 3/8. Oh, well, this isn't all that hard. If I make my sample space correctly, counting was actually fairly simple. Again, understand, I would only do this if the sample space is small. If the sample space were huge, we actually have to use the calculator to do everything. We don't need a calculator for this. Now, how many have exactly 2 tails in them? I'll put a little arrow this time just so you can distinguish. There's a 2-tail outcome. There's a 2-tail outcome. There's a 2-tail outcome. So how many of these are 2-tail outcomes?
3/8.
3/8. Now, finally, there's only one outcome that has 3 tails. I think we all agree with that. And that would be this guy. There's only one. So that should be 1/8.
1/8.
1/8 plus 3/8 plus 3/8 plus 1/8 is 8/8 or 1. They have to add up to 1. If somehow or another these didn't add up to 1, that just simply means I miscounted. Okay. So this is called the probability distribution, because what's different about this than what we did last week? Last week we did the counts, the frequencies, but now we're doing the probability instead. So the frequency would be the numerator divided by the number in the sample space. So what we did last week when we did frequencies, everything was exactly correct. But if I said, oh, 50 people had the following outcome, I'd say, well, is that a lot or is that a little? 50 out of 50 or 50 out of 1,000,000. The problem with just doing frequencies is if I don't know how many are in the entire population, then I don't know. Like I said, I have 50 people with the following outcome. I don't know if that's a lot or a little unless I know how many people are in the entire population. So if I said, 1% of the people had this, or 0.5% or 50%, now I have a really good feel for how big, that particular outcome was. Okay, so this is a fairly simple notion. Okay, so simply counting, that's always an easy thing to do. Now, I'm going to give you some notation here and some vocab it will make this a lot easier in some cases to understand. So now that we've defined the basics of probability, sometimes we want to do more than one thing. So I'm going to, first of all, I'm going to draw a picture. All right. This is what is called a Venn diagram. And that's not scary. Venn diagrams are one of the most useful ways of determining what's going on here. Simple picture. So the concept of the Venn diagram, imagine every possible outcome is going to show up in this box. Now I'm looking at two different things going on, two different events. Keep it simple. One of them is event A. One of them is event B. Okay. And I'm going to say there's some overlap there. So it could be that event A could represent all of the people in San Diego County who have a car. B could be everybody in San Diego County that owns a dog. Who is in here then? If A is all the people in San Diego County that have a car, and B is all the people in San Diego County that have a dog, then who lives in this space here? Anybody?
People that have a car and a dog.
Beautiful. That is called, this part right here is called the intersection. A lot of you have heard that word before. I like to use the word overlap as well. Those are the dog owning car drivers. Okay. Who lives in this portion? I'm sorry. I said A was cars, B was dogs. Who lives in this portion right here? Just this
People
part.
who
here.
only have cars. People who have cars and no dog.
Perfect answer. Who lives in this portion right here?
People who have a dog and no car.
Now, somebody else. Who lives out here? People who have
Neither.
neither. That's it. Would you agree then, in simple terms, that every single person in San Diego County fits into someplace here? This is car, no dog, dog, no car, both car and dog, neither car, no dog. Okay, that's so the Venn diagram gives me a really simple visual. Now, if I wanted probabilities we said before have to add up to 1, but sometimes we have to be a little bit careful. So intersection is the overlap. I'm gonna write it like this. What if I take everybody combined? I take these two circles and I combine it. That's not the overlap, that's I'm putting everybody together. So if I put the whole two circles together, there's another word that goes with intersection. If I did this, then we know what that's called. If I take all of it, that's called the union. So when I have these two circles, if I take all of it, that's called the union. If I only take the part that's overlapping, that's called the intersection. So let me give you a simple example. Okay, I have in my Calc 3 and my linear algebra this semester, as always, I have several students who are taking both classes. Okay, that's really common for them to double up. So what I want to do is I want to have a math party. Okay, and let's just say really simple. In my 252 class, I have 35 people. In my 254 class, I have 30 people. And let's say that both, I have 10 people. Keep it really simple. I want to have a math party next weekend, you know, crazy party, out of control. We'll have a bouncy house, you know, probably a clown or no clowns there, never mind. But, you know, we'll playing math games, and I want to invite everybody in both classes. So I send out an invitation to my entire 252 class. And then separately, I send out an invitation to my entire 254 class. And let's say everybody shows up. Awesome. This is going to be a crazy party. How many people are going to show up to my crazy math party if I've got 35 in this group and 30 in this group, but 10 in both? And everybody showed up. So is that going to be 75 people? What do you think? This is not obvious, is it? I got 35 people in the one class, I got 30 people in the other, and I got 10 people who are actually in both classes at the same time, and I'm sending an invite to everybody. How many invites am I sending out then?
65.
65? So in other words, are 65 people are going to show up? Maybe that's a better way of saying how many people are going to show up if everybody shows up? Is it 65 people? There's 10 people in both classes. So would you agree that 10 people got 2 invitations? Because they got one for each class. Is everybody cool with that? 10 people got 2 invitations. What do you think?
Would it be 35 plus 30 minus 10?
Why would I subtract 10?
Because they're gonna be because 10 are in both classes.
And I sent everyone in both classes an invite. These people got 2 invites, but when every one of these people shows up, don't they only count as one person? You don't count as 2 people. So you're absolutely correct, Rosalind.
Oh,
If I simply added these 2 numbers up, then I counted these people twice, didn't I?
yes.
Ah, so you're absolutely correct. And this is the mathematics of having intersections. So what I want to do in this case here, I'm going to use the same example. I'm going to use these numbers here. So let's say in this example that now A represents the 252 group, B represents the 254 group, and then 10 would be the intersection. Tell me what's wrong. I'm going to do something, and this is incorrect, by the way. I'm going to put 35 here, I'm going to put 30 here, and I'm going to put 10 here. So how many people are showing up to my party? Well, it sure looks like 35 plus 10 plus 30. That looks like 75 people are showing up to my party. But Rosalind just said, no, it should only be 55. And by the way, you're absolutely correct. There's only 55 human beings between these 2 classes because 10 of them are in both. But my picture makes it look like there's 75 people. Do you agree that there's something wrong with the picture? So what should we do? I'm going to show you because this is very important to understand. There are 10 people that are in both. Going back to here, if there are 35 people in this class, but 10 people are in both, how many people are in 252 only? How many people are only in Math 252? Anybody want to try that? There's 35 people in this class, but 10 of those people are also in the other class. So how many people are only in 252?
25.
25.
There are 25 that are only in 252. These are the 25 that are only in 252. These are the 10 that are in both. And doesn't that make 35 people in this circle now? Does everyone see that? There are 35 people in the 252 circle. So that's accurate. Now, there are 30 people in 254, but 10 of those folks are in both. So how many people are in 254 only?
$20.
20. Oh, now look. There's 35 people in the 252 circle. There are 30 people in the 254 circle. 10 are in both. So if I add up all of the people, that now adds up to 55, which is what Rosalind said it should be. And that is correct. So this is not an automatic, obvious thing. When there is an intersection, always start by counting in the intersection and then sort of work your way backwards. So now I want to introduce some notation that just makes this sort of easier. Okay. So I'll leave this for a moment. There's a symbol for union. There's a symbol for intersection. And you guys might remember this from lower level classes. Union, we use this symbol. Does anyone know what the symbol for intersection is? If that's the symbol for union, does anyone remember the symbol for intersection? There's a mathematical symbol. This is kind of like a big U. Same symbol, upside down. That's the universal symbol for intersection. That's the universal symbol for union. And the reason we like those symbols is just less writing. But that doesn't help me if I'm using English. So are there words that mean? Now, we said this before. Who lives here? These are the people that are taking 252 and 254 at the same time. So intersection, the word would be and. If you're doing this and this at the same time, that means you're doing both. That would be intersection. Union, you could be in this group, you could be in this group, you could be in this group. This group, people here are not here. People in this group are not here. But if you could be in any of these groups, then you could be in this group or this group or this group. The word here is or. And the words and or, mathematically speaking, are two of the most important words of all, believe it or not. Has anyone in this class ever done any kind of computer programming? You know, you had to write computer, whether it be for a high school class, a college class, you had to write program, you know, in a particular, in any language. Maybe it was C, maybe it was Pascal, maybe it was, you know, has anyone here ever, just say out loud if you have, you've written computer programs?
AP Computer Science, yes.
So the words and or, do they mean the exact same thing in computer terms, or are they kind of hugely different?
They're completely different.
Yeah, in fact, there are three words we usually say, and or, and probably the most important one, not, which we're going to get into later on. In a computer logic situation, those words are hugely important. So I'm going to give you a simple example of and or, okay? The word or is very inclusive. So if I give you a situation and I use the word or, if any part of the or is true, it's all true. See, it said, I want to invite all of the students that are in Math 252 or 254. That means I'm going to invite these guys, I'm going to invite these guys, I'm going to invite these guys. If you're in anything, either one of those classes. Or is inclusive. If any part of an or is true. So these people that are in 252 but not in 254, they're getting invited. These folks that are in 254 but not 252, they're getting invited. The folks in both, they're getting invited because I said you're in this class or this class. The word and is very exclusive. Everything in an and has to be true for the and to be true. If any part of an and isn't true, it's not true. Let's suppose I messed up my invitation. I'm inviting all of the people that are in 252 and 254. And I have this huge crowd, you know, I'm hoping for. I have all of this dip. And, you know, like I said, I got that super giant bouncy house and I rented a pony and all this stuff. And I said, I want all the people that are in 252 and 254. How many can show up to that party? Anybody? 252 and 254. I just described the intersection, didn't I? These are the only people that are in 252 and 254. Oops. And meant the people, you had to be in both to be the and. Now, this is very important from not only from a logic standpoint, but also from when I'm trying to calculate. And means everything is true at once, or means any part of it can be true. So here's the situation, all right? Last week, I went for a job interview. Okay, so like any good interview, I'm going to interview the people interviewing me. See, so when I show up, there's the long table with all these serious looking people, you know, staring me down. And I walked in and I said, before I work for you, I have a list of demands. Okay. I want my own parking space. I want an office window. I want keys to the executive washroom. I want a 6-figure salary, and I want the letter M stricken from all company language. Again, my own parking space and an office window and keys to the executive washroom and a 6-figure salary and the letter M stricken from language. And they get together and they talk about it and they say, we can do everything except the letter M thing. Am I going to take the job? Anybody?
No, you're not gonna take the job.
Why? Because I used what word?
You used and a lot.
I used and. Because I used the word and, all things had to be true or it's not true. They said we could do all of those things except the letter M thing. So therefore I cannot take the job because I said this and this and this. I I described an intersection. So next week they call me back for a second interview, and I kind of come back with my tail between my legs. I said, I've rethought. I want the parking space, or the office window, or keys to the executive washroom, or the big contract, or the letter M thing. And they come back immediately and they said, we can do keys to the executive washroom. Will I take that job? Again, I said,
Yes.
parking space, or window, or keys, or salary, or letter M. They offered me the keys to the executive washroom. Am I taking that job? Anybody? I gave 5 demands and I connected them with or. And they said yes to one of them. Am I taking
Yes.
that job?
I'm
Yes,
taking the job.
because I used the word or.
Mhm.
Oh, if I use the word or, only one thing has to happen. No, they could all happen, but only one of them has to happen. If I use the word and, they all have to happen, because or is the union and is the intersection. So understand, when we use words, it's very important that we understand which one, which thing we're doing. So is there a formula? Now, when we said how many people were all together, I wanted the people in the union, okay? Rosalind correctly explained that we had to subtract out the 10 because they were double counted. So how do I write that mathematically? Here's how we write it mathematically in any picture. If I said, what is the probability of the union of 2 events? Here would be a perfect picture for the union. That's where and by the way, that would be, we use the word or. What's the probability of A or B? Well, clearly it's the probability of A plus the probability of B. That's kind of a no-brainer. But wait a minute, we counted the intersection twice, didn't we? So we would subtract out the intersection. And this is the universal formula. If I want the probability of an or a union, I add up everything and I subtract the intersection, because the intersection got counted in both. See, the intersection got counted here and it got counted here, and I don't want to count it twice, so that's why I subtracted. So let me give you a really simple example, all right? Okay, so you did a recent poll of San Diegans, okay? I mean, not really, but hypothetically, you did a recent poll of San Diegans, and you asked them 2 questions. You asked them, are you still Charger fans? And the second question you asked them is, did you watch the Super Bowl? Because you're really interested. So you have an next door neighbor who, like me, who had seasons tickets for 40 years to the Chargers. And I can ask them, are you still a Charger fan? The answer is yes or no. Did you watch the Super Bowl? Yes or no. Those are 2 separate questions. Now, what you found was, in your poll, and you did a very extensive poll, you asked people all over the place, you found that 30% are still Charger fans. You found that 60%, actually, you found that 80% of everybody you asked watched the Super Bowl. And you found that 20% are both. So you did a poll of San Diegans, and here's what you did. You asked the person, are you a Charger fan? Yes. Did you watch Super Bowl? Yes. Are you a Charger fan? No. Did you watch the Super Bowl? Yes. Are you a Charger fan? Yes. Did you watch the Super Bowl? No. Are you a Charger fan? No. Did you watch the Super Bowl? No. Those are the possible outcomes. Okay. And you did a very thorough and extensive poll. So the question I would like to know is, find the problem. Now, again, I said, call C the event that somebody is a Charger fan. Call S the event that somebody watched the Super Bowl. Let's make it simple. I want to find the probability of C or S. Now I'm going to use the word or. I would like to find this probability. based on this. So take a moment. I want everyone to try this and I want you to tell me the answer, because I want you to be able to explain this to another human being, how you actually came up with that crazy answer. Now, I'm going to also draw a picture, okay? You have all the information. I'm going to draw the picture up here. I can't wait till we're back in the classroom when I have 50 feet of boards. All right. That's C. That's S. Now remember, a probability and a percent go back and forth. 50% is a probability of 0.5, right? 20% is a probability of 0.2, that sort of thing. So probably a good idea to fill in these things. So I mentioned before, what kind of order? Does anybody think they have an answer to this question, by the way? What is the probability that somebody did both? You're a Charger fan, or I'm sorry, not both. Sorry, I said that back. What's the probability you're a Charger fan, or you watch the Super Bowl? Anybody want to try that one?
I'd say it's about 20%.
Well, based on the numbers that I
fans
gave
at
you,
least.
I gave you the numbers, so it's absolute. It's based on the numbers I gave you. What's the probability that you are a Charger fan or you watch the Super Bowl? I said 30% of San Diegans are still Charger fans. 80% of San Diegans watch the Super Bowl, and 20% are both Charger fans and you watch the Super Bowl. So we're not saying they're completely separate. So if I asked you the question, I'd say, are you a Charger fan? Yes or no. Did you watch the Super Bowl? Yes or no. If you said yes to both, then you're one of the 20% who were both. But if you said yes to either, then you're clearly in both groups. Does anybody anybody want to try this? I don't want to guess. Anybody think they know?
10% that you're a Chargers fan and 60% that you watch the Super Bowl.
But so the question is, what's the probability you did one or the other? Well, if 80% of the people watch the Super Bowl, then the probability you did one or the other has got to be at least 0.8, doesn't it? Might be bigger. Now, I like what you were saying. You were telling me how to do the breakdown. So let's do the breakdown. What number do I put here? What number goes right here? 20% both.
0.2.
So 0.2. 30% of San Diegans are still Charger fans, but I've already counted 20% of them right here. So what's going to go right here? If 30% are still Charger fans, then how many are right here? This would be you're a Charger fan, but you didn't watch the Super Bowl. Well, if this has to add up to 30%, what goes here?
Point
0.1. Yeah, you guys are thinking way too much here. Now, you already said the answer to this. 80% of the folks watch the Super Bowl. I've already got 20% of the folks right here. So how many are out here? If that's 80% of San Diegans right there. So how many are out there?
0.6.
0.6. Great. Now check out my picture. 30% of San Diegans are Charger fans. 80% of San Diegans watch the Super Bowl. 20% of San Diegans did both. By the way, who's in the Netherland? Let's call it the Netherland. Oh, yes. You're not a Charger fan, and at the same time, you didn't watch the Super Bowl. You, boy, were just really lonely on Sunday, I guess. Okay. There are people out there like that. You don't want to hang out with them, but So what's out here? What's left, in other words?
Probably like the fans who don't watch football at all, at least.
Well, I want a number though.
I'd say wouldn't it be 0.3?
Well, that's 1 plus 2 plus 6. That's 0.9 so far. So wouldn't that only leave 0.1 out here? Remember, all the numbers have to add up to 1. So the question was this. Does everyone agree that the answer then is going to be 0.9? I mean, I can look at my numbers. Does everyone see that the answer is going to be 0.9? 90% of the people did one or the other. There was 10% of the people said I'm Charger fans, but I didn't watch the Super Bowl. 60% of the people said I watched the Super Bowl, but I'm not a Charger fan. 20% of the people said I did both. That leaves only 10% of the people that did neither. Now, we did this by drawing a picture and then filling in the numbers. Would there have been an easier way to do this? Yes. Yes. Let's write it down. The probability somebody's a Charger fan is given as 0.3. We said 30%, that's 0.3. The probability somebody watched the Super Bowl, we said, was 0.8. The probability that you did both, that's the intersection, is 0.2. Therefore, the probability that it's an or, that's union, I'll write it here. The probability that you're a Charger fan or you watch the Super Bowl must be this plus this minus this. That's the formula we just did a moment ago. And as Rosalind said earlier, you subtract out the intersection because you counted it twice otherwise. 0.3 plus 0.8 minus 0.2. That's my 0.9. Now that would have been a little easier just doing that. I drew the picture so that it would make sense to us, but that's what I actually have to do is right here, and then this is 0.9. Now, if I'm not paying attention and I just simply added these two up, 0.3 plus 0.8, can anybody tell me why you know that's a bad way to go? The probability that you either watch the Super Bowl or you're a Charger fan, and you just simply added 0.3 to 0.8. Did anybody see a potential problem with that? I'm hoping you
Well,
do.
it's 1.1.
And what's the problem with that?
That's more than 100%, which is
That's more than 100%. That's impossible. Oh, probability can't be bigger than 1. That's impossible. In fact, we have a really simple way of saying things. If something is absolutely certain to occur, I'm going to flip the coin. What's the probability it lands? Not heads or tails, it just lands. I'm pretty sure it absolutely is guaranteed to land. The probability of something that is absolutely certain to occur is 1, because that means your event is the sample space. Now, what's the probability that when I flip the coin, it turns into a duck and I eat that duck for dinner on another planet? I'm pretty sure that cannot happen. I'm pretty sure that's an absolute impossibility. What would be the probability of an absolutely impossible thing? Anybody? Absolutely impossible, cannot occur.
0.
Therefore, all probabilities are between 0 and 1. That's it. If it's absolutely certain to occur, has to occur, 1. Cannot occur. I'm going to flip a coin 2 times. What's the probability I got 27 heads? I only flipped it 2 times. You can't get 27 heads. That's impossible. That would be a probability of 0. I'm going to flip a coin 2 times. What's the probability I got 0 tails or 1 tail or 2 tails? The probability would be 1 because I just covered every possible outcome. So understanding that probability is a number between 0 and 1, it's usually reported as a fraction, but it's absolutely correct to report it as a decimal. And when you're speaking, sometimes people use percentages when they're speaking. Okay, I'm going to flip a coin, a fair coin. That means it's equally likely to be heads or tails. So we say, if I said I'm gonna flip a coin, heads or tails, do you ever hear the term it's 50-50? Does anybody ever hear that term? It's 50-50. I'm sure one of you has heard that term, right? Somebody who's wise and seasoned. You've heard that term.
Yes. Yes.
What are we saying when we say something's 50-50? What does that actually mean? I mean, we say things like that all the time. Are you going to the store today, Rosalind? It's 50-50. we say that. What are we saying?
50% chance that I will go.
And 50% chance that you will
Not go.
So a coin flip It's 50% likely to be a head, it's 50% likely to be a tail. In other words, the probability is 0.5 in either direction. It's 50-50. When we use words like odds, which I'm not going to go in heavily, but we'd say the odds are 1-to-1, 1 for, 1 against, equally likely. If we say the odds are 10-to-1, that's not very likely. It's 10 against, 1 for. So when we say words like 50-50, we are saying the probability is 0.5. I'm just as likely to do or as to not to do. Okay, but if something's absolutely certain, we don't say 50-50, we say, yeah, it's going to happen. It's absolutely guaranteed to happen. So we've started the basics of probability. We're going to take a short break here because we're going to now change to the next thing that we're going to do, because we actually want to be able to do some simple calculations. We're not actually really calculating. I'm giving you these numbers, right? You didn't calculate any of these. I said, here's the probability, 0.8, or here's the probability, 0.2. Now I'm going to ask you a question and you're going to tell me what the probability is. So it's going to involve calculation. So let's take a short break. And so from a standard deck of cards, they've been well shuffled. We're going to choose 3 cards without replacement. I do need you guys to always remind me to start the recording again. So here's what we want to know. Find the probability that all the cards, all 3, are red. Now, in a deck of cards, you have 52 cards. How many are red? Anybody know to start? Well, I only have
At
2
least
colors.
25 are red.
I only have 2 colors, right? Red and black. So how many are red and how many are black? Is it the same? Is it different?
It's isn't it 27?
Well, if I have 52 cards, how many red and how many black? Are they the same number or are they different numbers?
They should be different numbers.
You don't play a lot of cards, do you? No, it's actually half are red, half are black. Because we got the same number of red, same number of red as black. Yeah, exactly the same number. It'd be an odd deck if you had different numbers because which ones are. So how do you know? Well, easy way to remember it, the spades and the clubs are black, the hearts and the diamonds are red, and then there's the same number of each one. So in a standard deck of cards, you have 52 cards. Half of them are red cards. So exactly how many are red before I start? That's important. Exactly how many are red?
26.
26. Because remember, we're going to pull a card out and we're removing it from the deck. So that changes things. So what is the probability that the first card is red? That's easy. 26 out of 52. That's exactly 1/2. That's the probability the first card is red. I know Lila knows the answer to this one. What's the probability the second card is also red? Now, everybody should be on the same wavelength here. I just pulled a red card out and I set it down. What's the probability the next one is red?
25 out of
25
51.
over 52.
Over
51.
51, because
Oh,
I pulled it out of the deck. It's no longer there. Now what's the probability that the third card is also red? Keep going.
24
24
over 50.
50.
Beautiful. Now, I have a calculator. Here's something that everybody should know. Your calculator has a fraction key, and my calculator, it's right there. The fraction key is your friend. I can reduce this fraction tremendously, but I don't want to do that pencil and paper. That's way too much work. So on my calculator, I'm going to enter 26 over 52. That's what it looks like I'm using the fraction key, times 25 over 51 times 24 over 50. So I just entered the product of 3 fractions and I hit equal. And this is what my calculator gives me back, 2/17. I didn't have to do any work. I just had to enter the numbers. So when I multiply this out, it reduces to 2/17. Now, can I convert that to a decimal? Sure. That number there is perfectly good as an answer though. Now, what does that mean to me? Well, that's not a very big number, so it's not very likely that I'm going to pull out 3 straight red cards. Okay. But the idea is Your denominators changed because your sample space got smaller with each choice. That's huge. Now let's do the exact same problem. Same problem, dot, 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 but this time with replacement. I pull out a card, I look at it, I put it back in the deck, I reshuffle the deck. I pull out a card, I look at it, I put it back in the deck, I reshuffle the deck. Am I going to have the exact same three values here? What do you think?
No,
No. What's it going to be? Well, the first card is clearly this. What's the second one?
26 over 52,
Yes. And then the third,
26 over 52.
everybody see that? Why? Because each time I started over with the exact same set of 52 cards, so the probability stayed the same because I always put the card back in. That's just 1/2 times 1/2 times 1/2. That's 1/8. 1/8, 2/17. Which one is bigger? I can use a calculator or I can be clever. Isn't 1/8 the same as 2/16? Do you agree that 1/8 and 2/16 are the same?
Yes,
So 2/16 versus 2/17, this has a smaller denominator. So this one's just a little bit bigger than this one. That's an easy way to compare. I'm lazy. Okay. So when I pulled with replacement versus without replacement, it was a higher probability with replacement because I always had more red cards. Here's another way of thinking about this. What if I said, just keep pulling out cards, just keep pulling out cards. At some point, are you going to run out of red cards in the first situation? Will you eventually run out of red cards?
Yes.
But in the second one, will you ever run out of red cards? No.
No.
So believe it or not, the second one is exactly the same as a coin flip. It's like saying tails, 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 because my probability was always 1/2. Now, is this complicated? No. Do you need a calculator? Yes. I do not want anybody to do this pencil and paper and scratching and canceling and reducing. No, 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 no. Write your fractions, use your calculator, because all of your calculators, no matter how cheap, they all have a fraction key. I love the fraction key. Gets me off the hook for all this additional work that is just not necessary. And when you're simplifying an answer like this, you do want the fractional answer. You can always convert the fraction to the decimal, but you're not going to be able to convert the decimal back to the fraction. That's not really practical. So first thing we did today, we talked about the definition of probability, and then we talked about the probability of OR. I have event A or event B. What do? I find the probability of A plus the probability of B, and I subtract out the intersection. That was for the OR. Now we're looking at what if I do consecutive things, then I just simply multiply probabilities. That's not complicated, but it's different. It's not the same. So the last example we're going to do today, we're going to do some dice. And I like doing things where we already know what are the possibilities. So what I'm going to do, first of all, is create what I call a dice roll chart. On exams, and I think I even did this on the quiz, I usually provide this chart because I don't want you to make it each time you do the problem. I have 2 dice, right? One of them has 6 sides, the other has 6 sides. Each one has the numbers 1 through 6. What are the possible outcomes? It is like this: 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. 2 and 1, 2 and 2, 2 and 3, 2 and 4, 2 and 5, 2 and 6, and so on. This is what a dice roll chart looks like. I'm pairing the numbers on each die. You don't need to write this down right now. I just need you to see it, and you can reference it. And I usually have it printed on, like I said, on the quizzes and on the exams. Now, I'm going to roll the dice. I haven't added the dice yet. I'm just going to roll the dice and say, what are my possible outcomes? Well, I have a 6 on one die and a 3 on the other. I have a 3 on one die and I have a 5 on the other. How many outcomes are possible? I have 6 on one die. I have 6 on the other. Exactly how many outcomes are possible? 6 on one, 6 on the other. Remember the multiplication matching rule? 6 times 6.
Possibilities.
There's exactly 36 possibilities when I roll the dice. Now, if I go down this diagonal, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, anybody who's ever played with dice, what do we call those? 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. If you're a Monopoly player, you know what that is.
Doubles.
Doubles, those are called doubles. How many doubles are there? 6. So just for fun, you're going to roll the dice. What's the probability you roll doubles? What's the probability you roll a doubles? Won't my numerator be 6? What's my denominator? We just did it.
36.
So the probability that you roll a doubles is 6 over 36. And that reduces to 1/6. Oh, so when I roll the dice 1/6 of the time, I should be rolling the doubles. So let's do sums, okay? Because when you're playing a game, and a game like Monopoly or something else, it's always the sum that we're interested in. In fact, most games that involve dice, most games, it is the sum. Now, I'll make it easy. When I'm rolling the dice, the probability is always going to have 36 in the denominator because there's 36 possible dice rolls. But now we're going to, by the way, all 36 of these are equally likely. But now we're going to add them. So what are the possible sums you can have when you add the dice? Well, what's the smallest sum? For those of you who are gamblers at heart, what do we call the 1/1? Do anybody know?
Snake eyes.
Oh, I love it. They're called snake eyes because when you look at the dice, you see 2 little dots. They're called snake eyes. What is the smallest possible sum when you roll the dice? 1 plus
2.
1 or 2. I can also get a 3, I can get a 4, I can get a 5, I can get 6, 7, 8, 9, 10, 11, or 12. Now, okay, if you know snake eyes, then you know this one. That's my favorite. Anybody know what double sixes are? It has a name. Boxcars. You guys ever heard boxcars? Double sixes are called boxcars because they look like two. I don't think they look like boxcars. You know, 2 train boxcars. That's what they're called. So you have snake eyes, you have boxcars. I don't need you to know that, but yeah, those are common terms. Now, exactly how many ways can I roll a sum of 2? Well, only 1. So what's the probability that I roll a sum of 2? 1 out of 36. Now, how many ways can I roll a sum of 3? Well, I can get a 2-1 or I can get a 1-2. So there's 2 outcomes that have a sum of 3. Therefore, that probability is, I'll write a little bit off to the side, 2 out of 36. Okay, you're going to see a pattern really quickly. How many ways can I roll a sum of 4? I can get 3-1, 2-2, or 1-3. How many ways can I roll a sum of 5? You notice I'm just partitioning it like this. 4-1, 3-2, 2-3, 1-4. That would be 4 over 36. How about a 6? I think you guys are starting to catch on here. What do you think? How many outcomes? How many outcomes have a sum of 6? How many ways can I roll a sum of 6? Anybody? Nobody? A sum of 6? How many ways? You guys still here? I can wait. How many ways?
Isn't it 20?
How many ways can I roll a sum of 6? How many outcomes do you count there?
5.
5. Yeah, that wasn't all that hard, was it? So the
Yeah.
probability is 5 over 36. You guys see a pattern here? I hope you see a pattern here. Now, the most common outcome when you roll the dice, the one that has the most possibilities, is the outcome of 7, a sum of 7. How many ways can I roll a sum of 7? Exactly. How many ways? It's 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, 1, 6. So how many outcomes have a sum of 7? Again, you have a pattern developing here. How many outcomes? Anybody?
Six.
So the probability would then be 6 out of 36. Now, you see a clear pattern. So
Yes.
should this be, I'll just keep going. Should this be 7 out of 36 and then 8 out of 36 and then 9? Should I go like that?
No,
If I do, you know what? We're going to have a probability that is way bigger than 1 when I add them up. Oh, plus, wait a minute. As I go to the other side, shouldn't those be getting less? What do you think? I don't think this is correct. That is correct. Because now when I go to the sum of 8, I have 1 less. Oh, so what's going to happen to my probabilities now? They're going to start going the other way. I will go ahead and finish this off. There's only one way to roll a sum of 12, and that's double sixes. Now, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, that adds up to 36. So if I add up these fractions, they add up to 1, as they should. So every conceivable roll of the dice is represented, the probabilities of every sum. Now, every individual dice roll is equally likely. Is every sum equally likely? Yes or no? Is every sum equally likely? What do you think? Yes or no? Is every sum equally likely?
I say yes.
Well, do they all have the same probability, in other words? Is the sum of 7 just as likely as the sum of 12? No.
No.
There's 6 ways I can roll a 7, but there's only 1 way I can roll a 12. Now, the 12 and the 2 are equally likely. The 11 and the 3 are equally likely, and so on. But the individual sums pretty much are all different. Ooh. Now, I'm assuming you guys have probably played Monopoly before, right? If you've reached a certain age, it's unlikely that you somehow missed out on Monopoly. But Monopoly is a game basically controlled by the dice, isn't it? Now, I played Monopoly a lot when I was younger, and Monopoly is a game actually completely based on probability because everything's based on dice rolls. Some properties are more likely to be landed on than other properties. There are certain things that are more likely to happen than others because it's dictated by the rolls of the dice. Oh, so if we asked what's the probability of a certain combination of dice rolls, you can actually count them very simply. For example, okay, let's suppose I'm going to roll the dice. I'm going to roll the dice 1 time. What is the probability that the sum is at most, that's an important word, 5? Or I'll put it right here, at most 5. Now, we use words like at most and at least all the time in English language, but sometimes we misinterpret them. At most means 5 or at most 5.
5 or less.
5 or less, good. At least would mean that many or more. At most, I'm giving you the upper limit. So if I said I want the sum to be at most 5, then what am I asking? 5 or 4 or 3 or 2. Does that make sense to everybody? I want my sum to be at most 5. that means I'll put the probability of 2 or 3, 4 or 5. Now we saw earlier when it's an or, you add the probabilities. Now, you have to subtract out intersections, but here's the nice thing about dice rolls. I can't have a sum of 2 and a sum of 3 and have overlap. My sum is 2, my sum is 3. There's no overlap. Not in that case. Okay. So all I have to do in this case is take the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5, which in this case would be 1 over 36 plus 2 over 36 plus 3 over 36 plus 4 over 36. That would be 10 over 36 or 5/18 if you want to reduce the fraction. It is always a good idea to reduce fractions because sometimes they reduce tremendously. Now, you might be playing a game of Monopoly and you want to know, okay, I need to get a number at least this big or at most this big or somewhere in there. But we use words like this all the time, okay? So we say things like, what's the probability of getting at least this total or at most this total or exactly this total? Now, I'm going to leave this up for a moment. I'm going to give you a definition. It's sort of useful. Now, let me go back to my Venn diagram. I have two events, but this time I'm going to change it. I have two events and there is no overlap. There is no overlap. So it'd be kind of like saying A represents you went to work, B represents you didn't go to work. There's not an overlap. These are the outcomes where I went to work and I didn't go to work at the same time. That's not really a thing. So in this picture, the probability, I'll write it right here. The probability of my intersection in this picture is clearly 0. There is no intersection. This can happen. Okay, I can have situations where there is no overlap. That's actually not very hard to design that problem. You know, maybe I break up the class into everybody who is over the age of 21 and everybody who's 21 and under. Well, there's no person then in both groups. So if this is the case where the intersection is 0, or there isn't any, we say that the events A and B, I'm going to give you a new word. I'm going to put it right in the middle. We'd say that A and B are mutually exclusive. Some of you may have heard that term just in an English language. Mutually exclusive. I have two situations. You have to be in one or you have to be in the other. You cannot be in both. That would mean my two events are mutually exclusive. There is no overlap. Okay, that's not very hard to imagine a situation. I have situations where my events are mutually exclusive. If I said, I want you to roll the dice and your total is 7. I want you to roll the dice and your total is 12. Those are mutually exclusive events. There are no dice rolls that are both 7 and 12 at the same time. Okay, so that's an easy one. But what if I asked a question where there was an overlap? Sometimes you have to be clever and figure out. So here, I'm going to give you a really simple one. I want you to roll the dice. Okay, you're going to roll the dice one time and add it up. I want you to find the probability. I'm going to bring it to prob that the sum is a multiple of 2 or 3. A multiple of 2 means 2, 4, 6, 8, 10, 12. A multiple of 3 would be 3, 6, 9, or 12. Okay, just means you count by that number. I'm going to roll the dice one time, and I'd like to know what is the probability that my sum is a multiple of 2 or 3. Well, let's see. There's a couple of correct ways I can do this problem. One is I can just write down what are all the outcomes. So let's write down the outcomes. A multiple of 2 or 3. So 2, 3. How about 4? Would that be one of them? Yeah. How about 5? Is 5 a multiple of 2 or 3? Yes or no? Just holler it out. Is 5 a multiple of 2 or 3? Anyone?
No.
Nope. How about 6? Well, 6 is a multiple of both, yeah. How about 7? Is 7 a multiple of 2 or 3?
No.
How about 8? Well,
Yes.
definitely even numbers. How about 9?
Yes.
How about 10?
Yes.
How about 11?
No.
How about 12?
Yes.
Good. Oh boy, 1, 2, 3, 4, 5, 6, 7. There are 8 outcomes that I have to count, but you know what? I count this, so that should make it easier. I'm doing it the long way, just so you know. I'm going to show you a faster way. All right, 2, 3, 4, 6, 8, 9, 10. Okay, so what do we got? We got 1 over 36 plus 2 over 36 plus 3 over 36 plus 5 over 36 plus 5 over 36 plus 4 over 36 plus 3 over 36. One more, 1 over 36. Yikes, that's a lot of outcomes. So 1 plus 2, that's 3, plus 3, that's 16, 24. My answer is correctly 24 over 36, which reduces all the way down to 2/3. 2/3 is the best answer I can give because it's the simplest fraction. Okay. Now, everything I said was true and correct, but that seemed like a lot of work. It seemed like a lot more work. Maybe there's an easier way. Okay. Now, this is our last problem, so I'm going to erase the dice roll chart because we've already got it. What if I did this? What if I said, what's the probability that something's a multiple of 2? What are the multiples of 2? We just said 2, 4, 6, 8, 10, 12. Okay, let's do that. 2, 4, 6, 8, 10, 12. So that one, that one, that one, that one, that one, that one. I'm going to add them up. So 1 plus 3, that's 4. Plus 5, that's 9. Plus 5, that's 14. That's 17, 18 out of 36. Okay, that's 2, 4, 6, 8, 10, or 12. In fact, I'll even write those down. We just did that a moment ago. What is the probability something's a multiple of 3? Now, what are the multiples of 3? That would be 3, 6, 9, 12. So the multiples of 3 would be 3, 6, 9, 12. So 2 plus 5, that's 7, plus 4, that's 11, plus 1, that's 12. 12 over 36. But wait a minute. If I take 18 over 36 and I add it to 12 over 36, that's 30 over 36. What am we forgetting? I just found the probability something's a multiple of 2. I found the probability something's a multiple of 3, and I'm supposed to add those up. Are there any outcomes that are multiples of 2 and 3 at the same time? Is there any overlap? What outcomes are multiples of 2 and 3 at the same time? In other words, what numbers show up in both lists? Oh, I've double counted, haven't I? I've counted 6 and 12 twice. So the probability, I'll put both. That would be 6 and 12. That's our intersection. That's 5 plus 1 or 6 out of 36. Oh, so our answer should be this plus this minus the overlap. 18 plus 12 minus 6 is in fact 24 over 36. So if I don't take into account that there are roles that are both multiples of 2 and 3 at the same time, namely sums of 6 and 12, okay, so with dice rolls, we have to pay a little bit of attention. Now, it was absolutely correct to just list them all, but the problem with this is I might forget one. I might have left one out inadvertently. The only ones that we excluded, I think, were 5, 7, 11. We counted everything else, and that is correct. So this type of reasoning is always correct. Using the 2 and then subtracting the intersection is correct. Okay. Now we covered a lot of ground, but there's no difficult calculating. A lot of what we're doing really involves counting more than calculating. So we want to be mindful of this. So I'm going to go ahead and stop now. Let's see. We're running kind of long today, but that's okay.